In this video we will demonstrate the necessity of new rotational system to properly describe non-circular rotational motions. One of the simplest cases is elliptical motion with a constant tangential speed. Let's start with a superconductor puck freely levitating above an elliptical magnetic rail, and give it an initial speed. It will move with nearly constant speed, assuming the friction is negligible and the rail is well secured to the ground. It means that the only acceleration is purely orthogonal, which only changes the direction of the motion while preserving the speed. Here's one way of constructing an ellipse. Start with two perpendicular lines, then divide them equally. Draw lines from bottom corners to the line dividing points as shown. The crossings of those corresponding lines are forming an ellipse. Another way to construct an ellipse is by starting with two focal points. Points on boundary of the ellipse has equal sum of distance from both focal points. The diagram here shows a planetary system already known since Kepler, with notations of working forces and some important terminologies, like normal, tangential, and radial. Tangential force equals vector sum of normal force and radial force. In case of constant tangential speed, tangential acceleration is zero. Previous equation implies that the sum of normal force and radial force is zero as well. It means normal force and radial force must lie on the same line. By definition, normal line is perpendicular to the tangent line, while radial line must cross their rotational axis. In this case, the normal line is perpendicular to the elliptical trajectory formed by the magnetic rail. Thus, the rotational axis must lie on both normal and radial lines. Rotational radius is determined by the equation rot equals ds over d theta. Here's a method to approximate the position of rotational axes, which coincide with center of curvature for a given point on the elliptical trajectory. The arc from point 0 to 1 has center of curvature at point 01. The arc from point 1 to 2 has center of curvature at point 02. The arc from point 2 to 3 has center of curvature at point 03, and so on. More accurate positions can be obtained using smaller arc length. The positions can also be determined analytically using equations here. Let A be the semi-major axis while B is semi-minor axis. At semi-major axis, the radius of curvature equals b squared over a, while at semi-minor axis, the radius of curvature equals a squared over b. In the next video, we will show the geometrically identical trajectory of elliptical motion, but the angular speed is constant rather than the tangential speed. Comparison between both cases will clearly show the distinction between geometric and rotational radius. Stay tuned.